Hello, my name is Wendell Boucher. Today we're going to be talking about leakage inductance in that calculation for switch mode transformers. You can see here that the calculation of leakage inductance for a transformer using the G method is applicable to both high power audio transformer design and high frequency pulse transformer design and switch mode transformer design. Now the source of these G equations is this. It's a booklet over 700 pages long. The title of it is High Voltage, High Power Audio Frequency Design Manual. It's called a final report, and the work took from 1962 to 1964 to do it. Was published in 1964, and I prepared this presentation. Now here's some constraints. You've seen them before. They have to do with all calculations in transformers that use linear equations. You can't use linear equations unless the fields are linear, and you have to do this to make sure the fields are linear, both the electric field and the magnetic field. But today we're talking about the magnetic field. Here are the constraints. Number one, all winding layers are the same length, called LW, L sub W, sometimes called traverse, but I prefer this label. Number two, all winding layers are centered upon one another. Number three, the ratio of winding length, LW, that's this LW, divided, a few extra letters here, by insulation distance between pairs of windings is at least 30. Typically 50 or more is quite practical to maintain. Not hard to do this. But when you do that, you're pretty much assured that the magnetic field in the area of interest, which is where we're calculating the leakage inductance, is linear. So we can derive the necessary equations. And note that all dimensions are in inches. Here are the necessary equations right here. This is the first example we're going to show you, the primary, two secondaries. I'm not sure it's the first example. Let me look here and see. Yes, it is. So that's the first example. First we calculate a parameter called K1, or you can lump this all in with these equations if you want to, but I usually calculate K1 because it's a constant parameter which we multiply to other parameters in these regions and in the copper to get the leakage inductance. So for this example, the MLT, mean length of turn, would be measured here. Goes around a circle like this. Because you have the same winding actually over here, so it goes around a circle like this. But into the paper, coming out of the paper here. Okay? I'm sure you know what mean length of turn is. It's applicable also to capacitance calculations, DCR calculations, and so forth. Very fundamental parameter. It's in inches, as I said. First we calculate K1, which is 0.032 times the number of primary turns squared times the mean length of turn times divided by LW. That's a constant. And then LLP is going to be that constant times the summation of a parameter called A sub S and a parameter called A sub W. This has to do with insulation spaces. This has to do with copper wire. Now what we want to do was the same thing we did for capacitance parameter, is to reduce the H field, which is an ampere turns, to a value of 1 for the primary, and then scale the value for the other windings accordingly. Now, the AS is simply this number, provided that H of S has a value of 1 for the primary, which is showing right here, 1. This has to be 0.5. It's going to be 0. Didn't show it here, by the way. Let's see if I can do that. Yes, I can do it. Let me bring up the pen for a moment. Give you another number here. I have to find a view. Color picker, we make it yellow. And then we'll draw a circle. That's 0. The magnetic field outside of the tightly coupled windings is always 0, or pretty close to it. There'll be a little bit, of course, because it's not a perfect science. And so we show the H field magnitudes of 1, 0.5, 0, because these turns in the secondary are the same. I think I'll describe that a little bit later. So let's say this is what we have, a transformer configuration shown above. 1 primary winding and 2 secondary windings connected in series. All the windings are number 12 wire. Just an arbitrary number, of course. So the bare wire diameter is 0.0808. You look up in a wire table. In between the copper wire layers is an insulation layer. 2 such layers, each 0.05 inches thick. Here's how we set up and make the necessary calculations. Usually I do it this way, but I didn't do it this way here. I usually set up 5 regions in which to calculate the leakage contribution. Here are the 5 regions. 1 is that copper wire layer, if you will. 2 is the space between the copper layers. 3, this copper layer right here, or this one. Another space, which is here. And finally, another copper layer here. And then we're down to 0 again. Since we're going to use numbers which are called H left, H right, H right, you've seen this expression before. Those of you who have calculated capacitance of a transformer. It arises when you apply calculus to a straight line looking like this. So although it isn't an electric field, it's a magnetic field. It's the same shape though. So I've labeled the reasons here. For example, if we're doing the loss for this copper wire, we would use this equation. H left is the H on this side, H right, H on this side. And you can see it's 0 and 1. The next one is 1 and 0.5. So you can see 1, 0.5. The next one. For the third one, it's 0.5 and 0. 0.5 and 0. However, done it a little different way. I think you'll like it a little bit better. So here's what we have for the winding. MLT is 3 inches. If you use the UU64 core, it'll be about 3 inches. It'll be between 3 and 4 inches somewhere. I've arbitrarily picked a number of 20 turns of that number 12 wire, which comes out to be about 1.7 inches with an 1/10 of an inch or so. And the core is about the dimensions, as I said, as a UU64 core set. Then we can calculate the leakage LLP as follows. We start with that equation, which is K1, turns out to be 22.6 microhenry. Now that's not the answer, that's one of the parameters. But we're going to save that number because we multiplied times a lot of numbers. So now I'm going to show you another way of depicting this I think might be a little easier. Since when we're working with the wires we need a number, H field on the left, H field on the right, I decided to show you pictorially this way. Here's a primary, secondary, and secondary. Here's the H field, ampere turns. We made this one 1. This has to be 0.5. It's going to be 0. 0 here. So for this winding, we simply have 0 and 1. H left is 0. H right is 1. For this winding, H left is 1. H right is 0.5. For this winding, H left is 0.5. H right is 0. So let's take those numbers and show you this way. This is the calculation for this one, which is 0 squared plus 0 times 1 plus 1 squared, which is obviously 1 over a third, or 0.334. Alright, the next wire, talk about the wires now, just the wires. It's 1 on the left, 0.5 on the right, so we have 1 squared plus 1 times 0.5 plus 0.5 squared, 0.5 squared. That's 1.75 over 3, or 0.584. These are the numbers we want right here. The third one is 0.5 squared, that's the left. Here's the right. 0.5 squared plus 0.5 times 0, which is 0, plus 0 squared, which is 0. So it's simply 0.25 over 3, or 0.0833. Now, if we look at the LLP multiplier, wire multiplier, that's this number, 1. Now, if we look at for the insulation spaces, what do we have to do there? Let's go back and look at the equation for a moment. Insulation space is simply the H field squared times the distance S. S1 and S2 have to be 0.05 inches. I think I noted that somewhere. Yeah, right here. Okay. Go down a little further. And come up with those numbers. Then we say it's 1 times 0.05 and 0.25 times 0.05. Those are the S parameters. Then we come up with these two numbers, add them up, because we're going to multiply those times that K factor, multiply this times the K factor to come up with the inductance. And I didn't do it here yet, I'll do it a little bit later. Here's another example. Only got 7 minutes to go. We do the same thing exactly. Only now we have a secondary, a primary, and a secondary. This is called interleaving. Anytime you put a winding in between two others, which is their same logical winding, if you will, a secondary, this whole thing is a secondary, then you're interleaving. When you do that, two things happen. The magnetic fields get reduced. Because they get reduced, both losses go down and leakage inductance goes down. And here's how we do it again. Using the same numbers, doing the same construction. Here we come up with a different set of numbers, as you can see. They're smaller. This one, I think that one's about the same. No, that's smaller also. That's a smaller number. So is this one. Then we take that K factor, which is right here, which we found to be 22.6, and we simply do this. The space LLP multiplier, that means leakage inductor, refer to the primary. Coil 1 is 0.053885. I'm just repeating that number. There we came to up here. Okay. Now, so we calculate the leakage inductance stored in the insulation spaces. It's this number right here. This is for coil 1. Coil 1 is this winding configuration here. Coil 2 is this winding configuration. Interleaving. Supposed to be better. You'll see it is. But here's coil 1. Do all the multiplications. and we get 24.524 microhenry stored in the copper wire. That's okay, produced by the copper wire, if you want to think of it that way. And for the second transformer, you see we get this number and this number. This number compares with this one. This number compares with this one. And when you add them up, look at them, you see the ratio of coil 1 over coil 2 leakage inductance wise is about 3.25 to 1. So we reduce the leakage inductance from roughly 24 microhenry down to roughly 8 microhenry. And what we're saying here is, you have probably heard that if you interleave windings, the leakage inductance will be reduced. That's true, of course. And this exercise is a good example. Before interleaving, the leakage inductance was 24.5, and after, the same transformer windings, the leakage inductance was only 8 microhenry. There's the ratio. Noticeable reduction. You will find articles that say that the reduction should be 4 to 1, kind of exactly. They're not really true, but sometimes I've seen 4 to 1, but sometimes it's less than that, as we're seeing here. The ratio here is 3.25 to 1. You want to make the calculation to do it. Now in closing, time is almost up. Give a little history regarding the general subject of calculating leakage inductance. Historically, first so-called high-frequency, high-power transformers were pulse transformers that were designed and manufactured for pulse radar systems, and I designed them. That's actually where I learned to do this. A very active business during and following World War II. These pulse transformers were designed to meet a pulse input impedance and a rise time figure at the same time. So the leakage inductance parameter and effective capacitance looking at the primary, most power supply designers look at those two numbers and call them parasitics. They're not really parasitic to the pulse transformer. They're actually parameters we have to design to. As I say, that's how I learned it, and then it enhanced with my experience. So what we often call parasitics, switch mode transformers, were actually parameters in pulse transformers. Another mistake right there. Which is the reason that anyone engaged in pulse transformer design can easily design switch mode transformers with relative ease. That's why it's not hard for me to do. And you really need a lot more explanation than this to actually do it. A lot more examples. Then you get the idea. This can just get you started. As for ratios of leakage inductance to primary, or better still, magnetizing inductance, which it really is, switch mode power transformers can be thought of as a subset of the pulse transformers I just said. The leakage inductance is off around 1% or so I meant to say, of the magnetizing inductance. This is acceptable even for hard switching converters, but we can do better, of course. Pulse transformers are typically designed to have a leakage inductance value that's as low as 0.1% of the magnetizing inductance. I've mentioned this to engineers throughout my career. They tell me I'm crazy, but I'm not crazy. Most of mine were about 0.1. And if we chose the proper winding configuration, we can realize this low inductance ratio, not ratio, in switch mode transformer also. In fact, the designs here do have a rather low leakage inductance value compared to the realizable magnetizing inductance. How you design your transformer depends on what you want or need for a given application. For example, the LCC resistor converter absorbs this leakage inductance. Hard switching doesn't. The higher the LLP problem for hard switching, the worse the problems become. This is the conclusion because I run out of time. Thank you for watching.